Hello everyone, this is yet another session for our subject Nanoelectronics, and in today's session we shall discuss about Coulomb blockade effect and the transistor based on this Coulomb blockade effect. I hope you have gone through the previous sessions and made the concept clear, right? So this is yet another electronic device based on nano structures. So let's begin without much delay. Well, when it comes to the semiconductor industry of the future, see, we have been scaling down following the Moore's law. We have been scaling down and we have reached pretty small dimensions. Now, what controls the future of the semiconductor industry may perhaps be our capability to control even the smallest amount of charge in a very small region. With what kind of accuracy, with how good an accuracy can you control a very small amount of charge in a very small region? Perhaps this aspect may control tomorrow's electronics, which means we are concerned about adding or even subtracting a single electron into an extremely small region. And it is this effect or this concern which has created the idea behind single electron transistors. So today our session is about single electron transistors. See, I am saying about single electron, which means extremely small charged particle, right? So the basic concept about a single electron transistor is the behavior of the zero dimensional nanostructure, such as the quantum dots, right? They have extremely small dimensions, so that I can consider them to be as small as a single electron, right? So single electron transistor is all about quantum dots, and the most basic property or the governing principle in this structure is associated with the Coulomb blockade effect. See, when your conducting material is very small, the potential basically increases even when there is just one electron added to it. So you have a very small region, already you have just 2 electrons in it. Now, since the conducting material is very small, even the addition, I am adding a third electron into it, even the addition of a single electron can change their electrical potential in a very significant manner. That's what. Now, as we have already seen in the case of Coulomb blockade effect, if you want SETs to have a proper operation, we need them to follow 2 basic conditions. First, the change in the electrical energy when an electron enters or leaves a quantum dot must be much larger than kT, Boltzmann constant into temperature, which in terms of capacitance we have C must be very much less than E square by kT. If you remember, we have come across this condition when we were discussing Coulomb blockade effect. So what do we need? We must ensure that the change in electrons energy must be much larger than kT. That's it. Another condition is that the resistance of the tunnel junction must be large compared to the quantum resistance. So we are ensuring the second condition so that we can avoid the fluctuations in the number of electrons in the quantum dot. So that you can avoid fluctuations in the number of electrons in the quantum dot. So you are thinking about generating or fabricating a single electron transistor. So the main component of the single electron transistor is a quantum dot, right? But see, if you want to fabricate a transistor, you must definitely need 3 terminals, right? One of these terminal must be the gate to give the control voltage, and other two must be a source and drain region. So even the single electron transistor must have all these three regions. Now the SET will have, the single electron transistor SET will have a quantum dot which is connected to the source and the drain electron through, I will show you the pic, which is this is the quantum dot connected to the source and drain region through the tunnel junctions, right? And the gate electrode here is coupled to the quantum dot by this insulating material, so that the electrons cannot tunnel through the barrier to the gate. Okay, now does this seem similar to a transistor? You have the gate region, source region and the drain region, and by applying the gate control voltage, you can control the current flow from the source or drain, making it a perfect transistor, right? Now see in the figure you can see the structure of a SET and the equivalent circuit in terms of electrical components. We can see that. See what have been done is, the quantum dot, they have a total energy Ne, is, and this we call as Coulomb island. See basically any tiny conductive material we call them island. So when it comes to quantum dot and single electron transistor, I call this thing as the Coulomb island, maybe based on the Coulomb blockade effect, right? And this is connected to the source and the drain region and connected to the gate voltage through this insulating barrier, which has a capacitance effect. I denote this by Cg, the gate capacitance. And here we can see the IV characteristics of our SET. Now how do we determine this IV characteristics? We are continuously applying a gate voltage along the gate electrode, and this applied voltage induces a charge in the opposite plate of a capacitor, obviously. Now this is compensated by the tunneling of an electron that enters the quantum dot. Now what can we observe from this IV characteristic? There is some kind of a relationship between this induced charge along the capacitor and this tunneling of electron, and this creates oscillations called the Coulomb oscillation. Now this oscillation is related to the current flow due to the charges that tunnel across our barrier. This is due to the current flow because of the charges that tunnel across our barrier. And these oscillations we denote them as the current variation between the source and drain with respect to the gate voltage. That is in fact the IV relationship, right? Now between these two consecutive peak 1 and peak 3, see points 1 and 3 correspond to two consecutive peaks. Between these two consecutive peaks, the number of electrons in the quantum dot is fixed between these peaks, and thus the current flow is 0. I hope this is clear. Between these two peaks, you can see that the current is negligible, right? Why is that so? Because the number of electrons in the quantum dot is fixed. Only when there is a tunneling occurring, which is there is a flow of electron, there is a sudden increase in current. Until the next tunneling occurs, there is no addition of electrons or subtraction of electrons, so there is no flow of current. That's it. Right. Now the periodicity of this voltage peak is given by the 1 electron variation in the total number of electrons in the quantum dot. So, this is what I have said right now. The periodicity of the voltage peak is given by 1 electron variation in the total number of electrons in your quantum dot. So, delta V equal to E by C. So, we can say that the capacitance of the quantum dot can be obtained by measuring the voltage difference between the two consecutive peaks. That's it. Right? So, I guess the idea about single electron transistor is clear. Why this transistor is so important? They depend upon a single electron transmission or tunneling. We saw the structure, structure of an SAT, their equivalent circuit, their IV characteristics. Now in the IV era we could find oscillations called Coulomb oscillations, some terms relating to it. That's what we have seen so far, right? Now let's see a few applications and things about SATs. So in fact we can generate a number of logical circuits based on SATs. It's a pretty easy implementation of logical circuits. And an example of an inverter is shown here. And here what we have done is we have represented each tunnel barrier by a resistance in parallel to a capacitance. And we can easily observe the output voltage from this kind of a device. That's it. So other than these logic circuits, we have various other kind of devices also. Maybe memory cells that we can develop using SCTs, just as in the case of MOSFETs. A huge number of applications are there. Right. Let's see what is the difference between SET and a MOSFET. So SET is basically, just as the name suggests, they are single electron transistors. So they help fabricating devices of a smaller and smaller sizes, and their power dissipation is again very small. And an important advantage of SAT is their high output impedance due to the resistance associated with our tunnel barriers. Because of the presence of tunnel barriers, the SCTs have very high output impedance. But a disadvantage is that because of the size of the quantum dot, the temperature operation, its capacitance should be made very small as possible. So that's about SCTs, right? So this session was purely about SCTs. We saw what was the need of SCT, their structure, their IV characteristics, that's it, and a small comparison. So by this we are winding up the electronic devices made from nanostructures. From the next session onwards, we shall focus on the optoelectronic devices, optical devices from nanostructures. So please make sure that so far you have understood the concepts. I shall also share the notes. Thank you.